Hi all, so welcome back to the lecture series in solving the previous year questions of GATE ECE. So this is the part 3 of the video, and we were solving the questions related to analog circuits, mainly the questions from BJT and MOSFET transistors, right. So today we will be solving the questions from GATE 2022, and this is the first question. So let me mark that. So this is the first question of today's lecture series. Yeah, so let us start. So the question is, consider the CMOS circuit shown in the figure. The substrates are connected to their respective sources. The gate width W to the gate length L, ratio W by L of the transistors are shown as shown. Both the transistors have the same gate oxide capacitance per unit area. For the P MOSFET, the threshold voltage is -1 volt and the mobility of the holes is 40 centimeter square per volt second. For the N MOSFET, the threshold voltage is 1 volt and the mobility of electrons is 300 centimeter square per volt second. The steady state output voltage V0 is. So the question is to find the voltage V0 of this circuit. So as shown here, we have a PMOS here in the above and one NMOS below, and sorry, yeah, and as you can see here, we will first see the below circuit, that is the transistor NMOS transistor. Here the voltage V0, that is output voltage V0, is connected to the gate here, right, and here also the V0 is connected to the gate of PMOS. Fine. So this is the VGS voltage of NMOS. This is VGS and this is the voltage VDS. So from the circuit it is clear that VGS is equal to VDS and that is equal to V0. Why? This node is connected to gate itself. So D and G is same and source is common to gate and drain, right? Yeah. So this is source, this is gate, and this is the drain. And if you see here, the drain to source voltage is the V0, V out. Okay, so VGS is equal to VDS. So this is first observation that we can see here from the given circuit, and from here it is clear that what is VDS, this is greater than VGS minus VT. Why? Because VDS is equal to VGS and VT is 1 volt for NMOS, right? So VGS minus 1 is definitely less than VDS. So this is satisfied. So this equation is satisfied, which means NMOS is in saturation, right? Okay. So what is the current ID? Then ID, say I will call IDN, corresponding to the current through the N MOSFET. Okay. So say this is the current IDN. Fine. So that IDN current is given as IDN equal to 1 by 2 mu n COX W by L, WL by L of the N MOSFET, okay, that into VGS minus VT square. Okay, so VGS of N MOSFET, VT of N MOSFET. So I will denote this as VGS as VGS N and VDS N, showing that it is corresponding to the N MOSFET. Fine. Yeah. Okay. So here it is given that mu n is equal to 1, sorry, not 1, mu n of the NMOS is 300, right? So 300 into COX is not given, well W by L from the figure is 1, right? And VGSN here is V0 itself and VTN is 1. Fine, so this is IDN. Okay, I will call it as equation 1. Now similarly, what is the current IDP? IDP is the current flowing through this transistor, the PMOS. IDP. Okay, so I can write like 1 by 2 mu n, not mu n, it is mu p, right? COX W by L of PMOS into, so it is VSG, right? VSG of P MOSFET minus the threshold voltage of the P MOSFET. Fine. So again I will substitute here 1 by 2 mu p is given, mu p is 40 from the question into COX. So COX of both the transistor is same. So that is what given in the question, right? And WL of P is 5. So that into 5 into VSGP. Sorry. Okay. So what is VSG? VSGP minus VT. Okay. So we'll find what is this VSGP value. Okay. From this circuit. So if I draw here the same circuit if I draw here, so here it is applied as 4 volt, okay, and this is connected to the V out, and below I have the PMOS. So it will be like this, right? Okay. Okay, so this is VSG, okay, VSGP will say, and this is VGS. Okay, so from this circuit, what is VSGP? So VSGP is the voltage between the Vs and the gate potential, or gate means the gate is same as V0, right? So between Vs and between the Vd or V0, that is the VSGP. So I can say, right, this potential, what is this node potential? This node potential is equal to 4 volt. So VSGP is equal to 4 minus, what is the voltage at this node? This node is equal to V0, right? So VSGP is same as, so I can, okay, so VSGP is equal to 4 minus V0. So I can substitute that here. Okay, so VSGP is equal to 4 minus V0, okay, minus VTP, mode VTP is minus 1 mode, right? So it is 1 square. Okay, so from so this is the equation 2, that is a current IDP. Now from the circuit, okay, from the circuit it is clear that, so I will draw here. So this is IDP and this is IDN. Okay, and what is this current? So this current is a current flowing to the gate. Okay, so we know to the gate the Ig is always equal to 0 for MOS, right? So it is 0 ampere. So which means IDP is equal to IDN. Fine. So I will just equate both equation 1 and 2. So on LHS it is for IDN, right? So I can write as 1 by 2 into 300 into COX into 1 to V0 minus 1 square, that equal to ID. So this is IDN, right? So this is IDN and that equal to IDP. IDP is 1 by 2 into 40 into COX into 5 to 4 minus V naught minus 1 square. Yeah, so I can cancel 1 by 2 COX both side, right? And if I equate this, so how it will be? Sorry. Yeah, so this 0 cancelled. So 5 will go 6 times here, right? So I'll get like, and this 6 will go 3 times here too. So I'll get 3 into V naught square minus 2 V naught plus 1 here on LHS, and this is equal to 2 into, right, 4 minus 1 is 3, so 3 minus V whole square, V naught whole square, so it is 3 square, that is 9 minus 3 2 is 6, so 6 V naught plus V naught square. Yeah, so this is what I will get. Sorry. So if I rearrange this, what I will get? I will get something like this: V naught square minus, sorry, not minus, plus 6 V naught minus 15 equal to 0, right? So like 3 V naught square on LHS and 2 V naught square on RHS, so 3 minus 2 is 1, and here it is yeah, correct. So yeah, so here it is on LHS 3 into 2 is 6, and on RHS is 2 into 6 12, so if I subtract it will be equal to 6, and I have 3 and 18 on LHS and RHS. So if I bring that again, I will get minus 15 on LHS. So if I solve this, I will get V naught equal to 1.898, or I will get minus 7.89 volt. Okay, so that will be the V naught value. So I need to solve this. Okay, I need to solve this quadratic equation. So on solving this, I will get, so which one is correct? So V naught is same as VDS. Okay, and VDS is always greater than VGS minus VT, and definitely it is a positive value, right? Positive polarity voltage, right? So I should select the positive voltage 1.898 volt, which is less than 2 volt. Okay, so from the option the answer is less than 2. Fine, so that is the answer for this question. Okay, now let us come to the second question. So again it is from GATE 2022, question 2. Okay, so the question is, the ideal long channel N MOSFET and P MOSFET devices shown in the circuits have threshold voltage 1 and minus 1 respectively. So this is an NMOS, it has VTN equal to 1 volt, and this is a PMOS, it has VTP equal to minus 1 volt. Okay, the MOSFET substrates are connected to their respective sources. Ignore leakage currents and assume that the capacitors are initially discharged. For the applied voltage as shown, the steady state voltages are, so I just need to find the steady state voltage V1 and V2. Fine, so we will consider first the NMOS case. Okay, so here, so initially it is considered that the capacitor is discharged, so the voltage across this capacitor will be 0, right? And this is 5 volt. So this is the drain, this is the gate, and this is the, oh sorry, and what happened? Yeah, and this is the source end. Okay, so, and what is VGS here? VGS. So if this voltage or this voltage is V1, right? This is gate voltage VG. VG is 5 volt. So what is VGS? VGS is 5 minus V1. Okay, VG minus VS. VS is V1, right? So initially initially V1 is equal to 0. Why? Because the capacitor is discharged. Okay, so definitely VGS is greater than VT. Okay, VT is equal to 1 volt. Fine, because VGS is equal to 5 volt. Now, since VGS is greater than VT, definitely this will be similar to like this. It's like a switch. Okay, so here at drain I have 5 volt, at source it is V1, and I have a capacitor. Okay, ideally it is a switch, but practically it is like a resistor. It has a resistance value. Okay, so what happens, this capacitor will start charging like this, plus minus. So definitely V1 increases, right? V1 will increase. Okay, so V1 will increase from 0 to 1, then to 2 volt, etc. Okay, so it will increment the value from 0 to value. So I can draw it like this, or I will draw here, right? So this is V1, so it will slowly increase like this. Okay, so when it increases like this, what happens, if when V1 is say V1 equal to 1 volt, what is VGS? VGS will be equal to 5 minus 1, it will be 4 volt, sorry, yeah. Okay, now V1 is 2 volt, VGS will be equal to 5 minus 2 equal to 3, right? Similarly, it will increase, and what happens when V1 equal to 4 volt, VGS will be equal to 5 minus 4 equal to 1 volt. So this is equal to VT. Okay, now any V1 greater than 4 volt, what happens, VGS become less than VT, or NMOS will set to off, right? So the capacitor will charge definitely, but it will charge till until 4 volt. Okay, and once it reaches 4 volt, there won't be any more charge extra, because like when the voltage increases, the NMOS will definitely will be switched off. So what is the steady state value, the voltage across V1, that will be equal to 4 volt. Fine, yeah. So that is, so if you see the option, there are two options, that is in C and D I have V1 equal to 4 volt. Okay, now we will see the case of PMOS. Okay, so I will draw the PMOS here. This one micro, again similar to the NMOS, it is discharged initially, and this voltage is V2, and I have 5 volt. So this drain, this is source, and this is gate, and at gate I have minus 5 volt. Okay, so what is here VGS? See here VGS is equal to VG is minus 5 volt, so minus 5, and S here is V2, so VGS minus V2. So so when V2 equal to 0, definitely VGS equal to minus 5, that is equal to, or it's not equal, it is less than the VT threshold voltage, that is minus 1 volt. So that is what we require, right? For PMOS, the voltage VGS should be less than VT, that is if it is threshold voltage is minus 1, if VGS is less than minus 1, definitely that PMOS will be on. Okay, so similar to the previous circuit, it will act as a closed switch. Okay, so this is V2. Okay, so if I apply a voltage minus 5 at the gate and 5 volt at drain, what happens? sorry, again the capacitor will start charging like this, plus minus. Okay, so V2 will increase. Okay, V2 will increase. Okay, so if I draw again, if I draw the, wait a minute, okay, if I draw this, so V2 will increase like this. Okay, to what value it will increase, we'll see. So like similar to that, if V2 equal to 1 volt, what happens? VGS will be equal to minus 5 minus 1, so it is minus 6. Okay, PMOS is on. Okay, similarly if V2 is 2, it is minus 5 minus 2, it is minus 7. And similarly minus 5 minus, if the voltage is 5, okay, if the capacitor charges to 5, it will be minus 10. So for all these values, the MOSFET is on. Okay, PMOS is on. So definitely for this case V2 will increment till 5 volt. And what about 5 volt? Definitely it won't. Even if the voltage increases, the PMOS will be on condition, but the thing is like the supply voltage is 5 volt, so it will definitely saturate at 5 volt. Okay, so for the case of PMOS, V2 will saturate to 5 volt. Okay, so in the option, the answer is, correct answer is V2 equal to 5. So answer is C, right? So this is how we solve this question. Yeah. Okay, coming to the next question. Okay, consider the circuit shown with an ideal long channel N MOSFET. The transistor is appropriately biased in saturation region with VGG and VDD such that it acts as a linear amplifier. VA is a small signal AC input voltage. VA and VB represent the small signal voltage at the node A and B respectively. The value of VA by VB is, okay, so the question is, it is this NMOS is biased with VDD and also we have VGG voltage. Okay, and the question is like to find the value VA by VG in small signal. So what we'll do, we'll just draw its small signal model. Okay, so here instead of drawing the pi model, I will directly draw with the transistor itself. Okay, so I have 2K here, I have 4 kilo ohm here, and in small signal what I will do, I just need to short circuit the DC voltages. So VDD I will short, okay, and here also at the input I have the input signal Vi and VGG I will short. Okay, so this will be the small signal circuit. Okay, not in pi model, just with transistor itself, and I need to find what is VA and VB. Okay, so I will find VA and VB. So what is VA? VA is the voltage from this node to the ground. So I can say like the voltage across this VA, and VB is the voltage across, right, from this point to ground. So I can say this is the VB voltage. Okay, now from the circuit, so this is the source. Okay, so we know this is the current ID, so it is biased to saturation, right? So there is a current ID and the same current ID will flow here. Okay, so since this is a small signal model, I will say like we have the small signal current ID flowing like this, the same ID will flow through the source also, because it is in saturation, right? So what will be from this circuit itself, I can write what is VA. VA is the current across the 4K. So here the current is flowing from top to bottom, so there is a voltage drop plus minus. So VA is minus 4K into the current ID, okay, and VB is the voltage across 2K, right? So current is flowing from top to bottom, so potential drop is plus minus like this. So VB is equal to 2K into ID. Okay, so what is VA by VB? VA by VB is minus 4K into ID by 2K into ID. Okay, so if it cancel, it will be minus 2. Fine. Yeah, so that's all. Thank you.